Hello, in this video we will talk about the spectrochemical series, and this is really a continuation of the previous video on electronic configurations. So let me kind of summarize the previous video first. So when you have a neutral metal, so like a solid hunk of metal, you have both the 4s and the 3d if you're in the first row. If you're in the second row, you'll have the 5s and the 4d, so on and so forth. So first row transition metals, 4s, 3d. Now, when that metal becomes an ion, the 4s orbitals are higher in energy now than the 3d, and so all of your electrons will dump into the 3d orbital. And then you'll lose some electrons because, well, now you have an ion, a positive ion, so some of those electrons go away. Then, when your isolated metal ion forms a coordination complex, your energy levels for the d orbitals will split even more. And in the case of an octahedral compound, we get this nice splitting. So we have 3 on the bottom, and so these 3 orbitals point in between the ligands, and so there's less repulsion. And then there's 2 on the top. Those 2 orbitals on the top point directly toward the ligands, and while ligands are either negative or electron rich because they have to have a lone pair, they bind through the lone pair. And then, well, your d orbitals have electrons in them, so they tend to repel. So if you jam your d orbital right at your ligand, which is the case for these top 2 up here, then they're going to be higher energy because they repel. Okay, so that's the old news. So the new news is about delta, the crystal field splitting for an octahedral compound. And so the value of this is determined experimentally. Experiments show that the delta for octahedral depends pretty much just on the ligand. If you've got the same metal, of course, it depends on the ligand. And even when you're moving around in the same row of the transition metals, then still it's dependent on mostly the ligand. I mean, there's a little change when you switch metal, but it's not as much as when you switch ligands. And this is also assuming that the oxidation state does not change. When you change oxidation states, then that changes things pretty significantly. And we do most of our talking about this relative to octahedral compounds because they're fairly common and you can get some interesting chemistry out of it. And so we tend to talk about this most. So the spectrochemical series is made up of these experimental determinations of how different ligands split the d orbitals for a metal ion complex ion, or a neutral metal complex, either one. And so we have this list. On the left is lower delta, and these little less than signs are saying that my delta is less than the one next to me. Right, so when you go all the way up this is the biggest delta. So you actually don't need me to say large delta, because you can figure it out. Oh, this one's the biggest of, what is it? Delta, yes. And so we call these strong field ligands, and then over here they're weak field ligands. And so the fun thing about the spectrochemical series is that it can be used to predict if your octahedral coordination complex is high spin or low spin. And so let's show that for an example. So say you have hexachloromanganate 2. So since I said manganate 2, that means the manganese is 2+. And then if you go and look at a periodic table, okay, so all the electrons are dumped into the 3D. So the neutral metal would have 7 electrons. You just kind of count from the left, count to 7. And then since it's a positive 2 ion, now there's 5 d electrons. And so we're going to put our 5 d electrons in the d orbitals that are now split by the ligand. And then the amount of splitting is this delta. And so, well, let's go find chlorine on the list. Oh, there it is. So chlorine is a weak field ligand. So that means it's a small delta. And what we mean by small is that it's small relative to the energy to pair 2 electrons into one orbital. And so instead of pairing these, they will promote the electron, or I shouldn't say it like it has agency. The electron will reside in the higher energy state because it's overall lower energy. Kind of weird to think of it. But anyways, the energy to pair these is more than the energy to promote them. And so as we go putting our 5 electrons in, the 4th and the 5th electron go in the higher energy state because that's overall lower energy than pairing them down here. Now, if delta was bigger, then it would make more sense to pair them than to promote them, and that's large delta. Now, unpaired electrons are what we call spin. And so when you have a low delta, you have more unpaired electrons. And so small delta is high spin. Little opposite there in terms of words, but when you look at it, it makes sense. Okay, so this is the case for octahedral compounds when you're not messing around with the metal itself. And let's talk about now some trends in these crystal field splitting values for octahedral compounds when you change other things. So when you increase the oxidation state, the charge, on the metal, delta is also going to increase. And the reason here is because you make your metal more positive, and your ligands are negative or electron rich. And so when you do that, it pulls them together more tightly, and this winds up increasing the repulsion that leads to this splitting of energy levels, and so then it makes delta larger. Hopefully that made sense. And then as you go down a column in the periodic table, delta tends to increase as well. I don't have a nice little explanation of why, but experimentally we've seen it. And so this table from Macquarie shows you some of these experimental numbers. So that's octahedral. This also happens for tetrahedral. And so in a tetrahedral compound, your order of your sets is reversed. So there's 2 on the bottom and 3 on the top. And the reason here is because, well, your ligands are sitting in different spots. So instead of your ligands sitting on the coordinate system axes, and the coordinate system axes are defined by your orbitals, so where your orbitals point. So here your ligands sit in between the coordinate system. And so the XY, YZ, and XZ ligands that also sit in between the coordinate axes repel more. And then your 2 d orbitals that sit on the coordinate system axes repel less. And then we have a delta tetrahedral. And now this effect, though, the difference between, on the axes and off the axes, is overall less for a tetrahedral compound because it doesn't quite line up directly. Whereas for an octahedral compound, your ligands are on the coordinate system axes. It really messes these ones up. Whereas here, the effect is not as strong, so the delta is always small. So a tetrahedral compound is always high spin. You'll always promote this before you pair them. Okay, we can do square planar also. And so square planar, your ligands sit on here. And then your energy level splitting looks like this. And it's pretty complicated. I don't do square planar in class because I think that's not really a helpful thing to learn. But I want to show you that this is different like this. And also if you have a linear compound, then you have yet another set of how your d orbitals split. So it really does depend on the geometry of your compound. And the ones that I focus on in class are octahedral for sure, and then tetrahedral kind of as a second thing that I like to focus on. Okay, but let's go back to talking about octahedral because we can use this as our framework to understand colors of transition metal compounds. And so, we did this in the first semester of chemistry with the hydrogen atom as well. And so your electrons were transitioning between these different energy states, or shells, really, n equals 1, n equals 2, n equals 3 for hydrogen. And that allowed it to absorb light. And so the same thing is true here. We have our d orbitals that are split into 2 sets, and then the energy difference, remember, is delta. And so if some light happens on this compound that is of the exact same delta, then it'll absorb into the system. And what it'll do is it'll take the electron that's in the lower energy state and put it up to the higher energy state. And then eventually, through some other means, the energy will get dumped out of this system, and then the electron will return back to the ground state. This is some sort of, rotations or collisions or vibrational changes or something like that. There's some other way that it stuffs the energy around. But it absorbs the light. And so the energy of light absorbed is this delta, right? So this is E. And then E equals h nu, whereas nu is the frequency, and h is Planck's constant. And this is one of our fundamental equations of all of physics, E equals h nu. And now we can replace frequency with the speed of light divided by wavelength and get to the wavelength. Now we typically use wavelength when we're talking about visible light because it gives us nice numbers. Oh, the wavelength is 500. And that's a nice number, so we do that. And then this wavelength for transition metal compounds is almost always, often, in the visible region of the electromagnetic spectrum, and so we can use that to our advantage. So now here's something else from the previous semester, right? First semester Gen Chem, we talk about absorbed versus observed. And so let's remind ourselves what that is, right? So the observed color, what your eyeballs see, is what's left over after your compound absorbs some color. So hexaquatitanium-3 absorbs yellow-green light, somewhere in the yellow-green, and hey, look, that's right here. And when this light's absorbed, well, then the rest of the light passes through it or reflects off it. But in the case of a solution, it's going to pass through it. And so when your eyes see all of the other colors except for yellow-green, then your eyeballs treat that like it's red, violet red. Right? So you go across the wheel, color wheel, to see what your eyeballs see, whereas what's actually absorbed is light of the wavelength that's yellow-green. And so another way to see this is imagine your sample like a filter that absorbs yellow-green light. When you shine white light on it, which contains all the colors, then you have all the colors except yellow-green on the other side, and then your eyeballs see that as purple. So hopefully that is old news, and if not, well, now I told you. So this is a fun figure from Macquarie that I like to throw up, not a figure, a picture, that has crystals of the chlorocomplexes of the first row transition metals, and pretty much all of these are colored. Zinc, however, is an exception. Zinc 2+ is the D10 ion, so the entire split D orbitals are full, and then there's no place for electrons to move, and so it can't really absorb light. Just found that interesting. Okay, so let's dig into this colors thing a little more. And so for the purposes of learning more about transition metals and seeing again how light interacts with compounds and electromagnetic radiation and colors, we talk about this. And so one thing we can do is compare how ligands will change, what color your complex absorbs, by looking at the spectrochemical series. So one way we can do this is just ask, hey, which one absorbs the highest or lowest light? And the other way we can do it is by comparing, right? And we're doing this again, that delta is equal to h nu, which is equal to hc over lambda. So when you increase delta, which is moving to the right on this list, then it'll decrease the wavelength. So one thing we can do is ask, hey, which complex absorbs light of the shortest wavelength? So you answer this question by first remembering that, right, the largest delta has the shortest wavelength, because delta is energy, which equals to hc over lambda. Okay, so now we're looking for the shortest wavelength, so the largest delta. So then you just look at these ligands and where they sit on the spectrochemical series. And if there's more than one ligand, you can kind of average the effects in your head. And I personally won't ever give you one where like it's a compound that has ligands from all over the place on the spectrochemical series, because this problem has to make sense, right? So okay, so then the one that's highest on the spectrochemical series, the largest delta, absorbs the lowest wavelength. And so that's this one. And so then our answer here is this cobalt compound on the bottom. Okay. The other thing we can do is think about comparing. And so either you have two compounds and you're comparing them, or you're doing a ligand substitution reaction and you start with the hexaaquacobalt-2 and then you dump in ammonia and then you get the hexaamine cobalt-2 ion. And so we can do that too. So if this compound appears reddish pink somewhere in here, that means it's going to absorb green. You don't know where on the range of green it is, what shade of green, you don't really know. But you know it's green, and for this problem that's good enough. And FYI, this is the color wheel that I put on the exam info sheet. And so it's the chemistry version, it has numbers of wavelengths around, which is nice. And another thing to remember is, right, these two aren't exactly next to each other in wavelength, so I put the little line here to say that it's about 400 nanometers at the end of the blue-purple end of the spectra, and 700 nanometers when you're in the red end. Just our eyeballs treat it like it's a circle, so we can draw it that way. Okay, back to the question. So this thing's green. It absorbs green, I should say. And we want to know what color the amine compound can be. So if we go to the amine compound, it's going to have a larger delta because amine is to the right of water on the spectrochemical series. And so that means it's going to have a lower wavelength absorbed. This list up here of wavelength is, largest is on the left, smallest is on the right. So when we move to the right, we've got a lower wavelength. And so that lower wavelength absorbed, say, all right, so we're at green over here, and then we go to a lower wavelength. If you look at the numbers, you see that going lower is over here. And I usually just move one color over when I'm doing these problems. For the simple examples we use in Gen Chem, that actually works out pretty okay much of the time. Not all the time, but sometimes. And so if this thing absorbs blue, it's going to look orange. So it will appear orange. And that's the answer to the question. So you do have to invert it across the color wheel a couple times in order to do these problems. But overall, I think it's a good thing to do educationally. And then we get to think about colors in transition metal complexes. So that's all I have for now. Thanks for watching.